Hello everyone. So we are now in a seventh session. This part basically has nothing to do with part one on dynamic system. This part is mainly to discuss, to introduce to you what you will need when you are going to design a controller. So this in this session, mainly the topic will be on basic control action. For this week, the learning objective will be at the end of this topic, you should be able to describe different types of controller that you are going to discuss more in part 2. We have already discussed a lot of things about systems in the previous few topics. Before you move later on the second part on discussing how to design controllers, in this very short topic, I will introduce to you how do we link what we have learned on dynamic system to controller design, the thing that you are going to learn in the next part. Okay. Talking about system. Okay, we are talking in particular about a mechanical system here. Talking about mechanical system, there are two different types of system that you might encounter. The first one is, I'm talking in terms of from the perspective of controller, of course, here. The first one is an open loop system. Please don't get confused with the terminology of open loop transfer function in our closed loop system, in our feedback system. What I meant by open loop system here, a system that is not controlled. So taking an analogy again to air conditioning system, the simplest example that I frequently discuss. If I'm referring to open loop system, open loop of an air conditioning system, then the best example is the heat pump of your air conditioning system. Imagine again, we discussed this in our very first topic. Heat pump is a part of your air conditioning system that will take out heat from one location to another location, right? Without putting your heat pump in a controlled system, in air conditioning, in a complete air conditioning system, your heat pump will just take out heat from one location to another location. And you don't like this, of course. If you put it in your room will become very chilled. Your heat pump is not controlled. So heat pump solely is an example of an open loop system. And as I mentioned, you don't like to use heat pump to cool down your room. Normally, in air conditioning system, we put heat pump together with controller and temperature sensor, right? So in air conditioning system, your heat pump will be put together with a controller. And sometimes you can also consider sensor in here, right? Of course, in most of the cases, we can neglect the transfer function of the sensor because normally sensor has a very good accuracy, very high bandwidth, so we can consider sensor as an ideal sensor with a transfer function of unity 1. So we can remove this part. So in this case, this is the example, the representation of the second type of a system, which is a closed loop system. You put your heat pump, which is an open loop system. It's an open loop system because you don't control it. You put this open loop system here and you combine it with a controller. As a result, you will have an air conditioning system, a heat pump that can regulate the how much heat will be taken from your room. Okay, so you might have an open loop system, a system that is not controlled at all, and a closed loop system, an open loop system together with a controller to form a closed loop system, a system that can be controlled. Talking about advantages and disadvantages of these two types of system, if we are having an open loop system, the advantage of having an open loop system, if your system is stable, then your system will always be stable all over the time, right? The second advantage of having an open loop system is, of course, it will be less expensive. You don't need an additional component of a controller. You don't need a sensor. Obviously, it should be less expensive. The next one, open loop system, somehow I can say it's easier to control. Control is not a proper word perhaps here, because an open loop system is not controlled. But imagine if you are using heat pump solely to cool down your room. So you are not using a complete air conditioning system, you are only using a heat pump. It is easier to control. How to control it? If your room is too warm, you just turn it on manually. If your room is becoming too cold, then just shut it down. It's very easy, it's very simple, very straightforward. But of course, we don't like this. You cannot leave it run by itself. You have to manually tune it by yourself. So those are the advantages of open loop system. What about the disadvantages? If you have an open loop system, it is sensitive to disturbance. What do I mean by sensitive to disturbance? If you have a heat pump, let's say, you don't put it in a closed loop system to form an air conditioning system. Your heat pump, after sometimes, the performance might deteriorate. Let's say there will be a lot of dust covering your heat pump, and then after sometimes when everything is covered by dust, the performance will drop. Your heat pump is not performing effectively anymore. So it's sensitive to external disturbance. The second one is also periodic calibration is required. When dust is piling on your heat pump, the performance is dropping, you have to clean it. That's a kind of calibration. You have to calibrate it, you have to clean it, and many other things of calibration that you have to do to maintain the same performance of an open loop system. What about closed loop system? Of course, we have some advantages and disadvantages here. The first one, if we talk about the advantages, a closed loop system, when you have a system in a closed loop form, you will reduce the sensitivity of a disturbance inputs. What do I mean by that? Again, let's take the example of this heat pump. If you put your heat pump in closed loop system, then you have a real air conditioning system. When the dust is piling on your heat pump, then the controller logic, if you have a good air conditioning system with a good controller, the logic of the controller in your air conditioning system will ask the heat pump to take more heat when the heat pump is not performing well. So there is a way to regulate the heat pump through your controller in your air conditioning system to reduce the sensitivity to the disturbance. There is also another advantage. A closed loop system will reduce also sensitivity to change in plant. You can take the same example again. If dust is piling in your heat pump, basically your plant, your heat pump behavior, basically your heat pump performance, your heat pump dynamic behavior change. So the system change there, the plant, the system that you control change. If you put it in a closed loop system, the effect of the change of the heat pump of the plant that you control, it's becoming less sensitive. Even though the performance, the behavior of the system change, the performance of your complete system in a closed loop form will be maintained. Okay. And the third one is the ability to stabilize an open loop unstable plan. So for instance, you have a system, but your system, the plan is unstable. You can stabilize an unstable plan by putting it in a closed loop form. But of course, here you need to design a proper controller to stabilize an unstable plan. The next one is the ability to change the dynamic of the system. Let's say again you have the heat pump of your air conditioning system is not performing very well in terms of the speed. You need about an hour to cool down your room, you don't like it, and then if you design your controller properly, you can change the dynamics properties. You can make the system respond faster. Okay. But of course, few disadvantages you can note it here. You need sensors, you need a controller. Of course, this will cost an additional cost for that. You need to design a proper controller, so it adds complexity somehow to your system. Okay. And if you don't design the controller properly, you might make your system, which was previously stable, to become unstable. So designing a proper controller is also important. It's the main thing in this closed loop system. Okay, what you see in this slide is a common block diagram that you might encounter in industrial application. You have a plant to be controlled here, and if you run a plant, let's say again a DC motor, the simple one. If you have a DC motor, how you run the DC motor? You always put a power supply on it, right? And then if you want to control the rotation of your DC motor, you need to sense the speed of the DC motor, and then you feedback the speed that is read by the sensor to the controller. The controller here consists of an amplifier, the logic, the error detector. What I mean by error detector here, the part that compares the setting point with the actual output. So again, if we are taking an example of air conditioning system, the error detector is the part that will compare the setting temperature with the actual temperature of your room. So this is typically a block diagram in industrial application. Let's take a more detailed discussion on a closed loop system. But to make our analysis simpler here, let's consider a unity feedback system. You still remember what unity feedback system? Unity feedback is a system where the feedback part here, the part where normally we place the sensor, has a unity transfer function. Sensor, normally if you form a closed loop system, you normally use a very good sensor. And a good sensor, you can consider it as a static system because you have a good performance, such good, so the response will the output will respond immediately. So if you choose a very good, an ideal sensor, the transfer function of your sensor will be close to unity. In this case, then we can draw it like this, right? Okay, let's take this unity feedback system into our discussion now here. The controller part, you can design different types. There are many different types of controller that you can use in your closed loop system. Either it's a unity feedback system or non-unity feedback system. You can use many types of controllers. There are many tons of controllers, but the most popular ones are the one that I listed down here in this slide. The most simplest controller is what we call as an on-off controller. I will discuss this briefly in the next few slides. And a proportional controller integral controller, combination of proportional and integral, where we normally call it as a PI controller, combination of proportional and derivative controller or PD controller, or a combination of those three, proportional, integral, and derivative, where we call it as a PID controller. So we can use either one of these controller in combination with your controlled system to form the closed loop or feedback system. So this is the first type, the simplest controller. It's on-off controller. Actually, we have already discussed this kind of controller many times. The controller that we discussed when we were talking about air conditioning system. So on-off controller has only two fixed output of the controller, on or off. What do I mean by that? Okay, let's take an example of this air conditioning system again. Your controller will only have two actions. Either it will ask the heat pump to on when the room temperature is higher than the setting temperature, right? Or the controller will ask the heat pump to stop when the room temperature is colder than the setting temperature. So it only has two actions, on or off. So it's pretty simple in terms of the logic here. And if we want to represent this kind of action in more mathematical form, we can show it. You can see it as it is shown in the block diagram of this slide. Let's discuss about how this works from mathematical point of view. Okay, so again, this is an example of the on-off controller. We discussed this already before. When your room temperature is higher than the setting temperature, the difference is negative, the controller will ask the heat pump to start. Otherwise, when the difference is positive, the controller will shut down the heat pump. So it's just two action of controller. That's why we call it as an on-off controller. Let's talk a bit more detail from mathematical point of view, the action of this controller. Okay, again, owing to the concept of this air conditioning system, I want to describe this controller action in more scientific way. Then the controller, as what we know, of course, we discussed this many times, the logic of this controller will activate the heat pump, right, when the room temperature is higher than the setting temperature. So C is the room temperature, R is the setting temperature. Since if you look at this summing point, E is equal to R minus C. So I can repeat it again, the logic, the first logic, the controller will activate the heat pump when the E value is negative. E value will be negative when C is higher than R, right? Otherwise, the controller will deactivate the heat pump when E is positive, or when the room temperature is less than the setting temperature. Your room temperature is colder than the setting temperature, right? And then the controller will shut down the heat pump. In a mathematical representation, the logic of the controller can be presented this way. So again, if E is negative, saying that the room temperature is higher than the setting temperature, the controller will ask the heat pump to start. And I indicate it here as 1. So 1 means start the heat pump. Otherwise, when E is positive, saying that the room temperature is colder than the setting temperature, the controller will shut down the heat pump. And in mathematical way, I say 0. 0 means shut down the heat pump. So in mathematical representation, the logic of this controller, of this on-off controller, is like you see in this graph, right? U is the action that is the logic that is sent by the controller to the plant. So when U is 1, the plant, the heat pump will start. When U is 0, the plant will shut down. Let's talk a bit more about this on-off controller. Now, but I want to implement this on-off controller to different application. I want to control a DC motor or a motor in general. But what I want to control here is the position of the motor. Let's say I want to, what you see here is the shaft of the motor. And then I want to change the orientation of this shaft. So the current position is in here. And then I want to move it to this target. Okay. And then to do that, I need a controller. In my first attempt, I will use this on-off controller. But I changed the logic slightly from the on-off controller that I use in the air conditioning system. Okay, I will talk about this after this in a few moments. One thing that I want to mention here, let's take a notation that counterclockwise direction is positive. Okay, so this is the target. Target means the desired position, the setting position. So this is the R in our code, in our block diagram. This is the orientation of the shaft. So this is the orientation of the shaft, which is the output. So this is the C. If we have such a case, because counterclockwise is positive direction, so the E here, the error will be, which is R minus C, based on the summing point, E is equal to R minus C. In this particular case, right, when your target is on the counterclockwise direction from your current position, your E here will be more than 0. Okay. So in this case, your E is positive. And then I want to control this shaft orientation. My first attempt, I will use on-off controller. I use the similar logic to the air conditioning system, but I change it slightly. This is the logic that I will use to control this motor. So what I put in the controller using this on-off controller is that when E is positive, what does it mean? E is positive means the target is higher than the current position, which means the target is in the counterclockwise direction to the current position. I will ask, when E is positive, I will give a command of 1 to the motor, where 1 here means the motor has to rotate in a full speed in a counterclockwise direction. Otherwise, when E is negative, saying that the current position is in the counterclockwise direction relative to the target, the controller will ask the motor to rotate in a clockwise direction again in a full speed. So expectedly, when my current condition is like this, like the one that you see in the slide here, when the target position is still in the counterclockwise direction of the current position, the shaft of the motor will rotate in a counterclockwise direction until it reaches the target. And then it should stop, right? Because the error will be 0. Or if I have another case where the current position is in this direction, let's say, saying that the target is in the clockwise direction relative to the current position, the E value will be negative. The controller will ask the motor to rotate in a clockwise direction in a full speed. And then it should stop. That is my logic. It should stop when the current position is exactly equal to the target, where that means the E is 0. So it should stop. Yeah. Okay. But there is a flaw in my technique here in implementing on-off controller for controlling the motor here. When I run this motor with on-off controller, because I ask the motor, the controller asks the motor to rotate in a full speed. If you look at this, when the controller sees that the target is far in the counterclockwise direction of the current position, then the controller will ask the motor to run in a counterclockwise direction in full speed. What will happen? Because it is running in a full speed, it will miss the target. Intuitively, I say at this moment it should be okay, because if I miss the target, then the error will become negative. If the error is negative, what does it mean? The motor will rotate into the opposite direction, to the clockwise direction. But again, look at the logic again. When E is negative, the controller will ask the motor to rotate in a clockwise direction again in full speed. So this is what will happen when the current position exceeds the target. It will rotate in a clockwise direction in full speed. And then it will miss again the target. The error is becoming positive again. So the controller will rotate again the motor to the counterclockwise direction in full speed. So again, it will miss again. And then that will happen repetitively. It will happen all the time. So instead of reaching the target, your motor now will oscillate within this target. It will never stop. It will never reach the target, but it will move back and forth like that. So this is not a good controller to me. The flaw that I see in this control strategy is because I asked the motor to run at the full speed. So what should we do? I had a smarter idea. That's what I thought. So what I will do, I will slightly modify this controller logic from this one previously. Right? I will modify it into something like this. Okay, so I changed the logic of the controller slightly into something like this. I thought it will work. So what do I do here? What does it mean? It means when the error is very high, at this region, the controller will ask the motor to run in a counterclockwise direction at the full speed. But then when the current position almost reach the target, the controller will still ask the motor to rotate in the counterclockwise direction, but with half speed, because it is approaching the target. So I want the motor to slow down. Same thing if the error is negative. When the error is still very large, I will run it. I want the controller to ask the motor to run in a clockwise direction in full speed. But when the current position is about to reach the target, I want the motor to slow down into half speed. Okay, so it should work. That's what I thought now. So when I run the system with this kind of controller, this what will happen. It still misses the target. Why? Because apparently half speed is still too fast. When it exceeds the target, now it will rotate in a clockwise direction. It still exceeds the target. So the same thing still happen. It's still oscillating within the target position. Why? Because apparently half speed is still too fast. So then I have another thought here. So why don't I change the logic of the controller? Instead of splitting into two regions of speed, full speed and high speed, why don't I split it into 4 regions? Full speed, 3/4 of the full speed, half speed, and only 25% of the full speed. So I chunk it into 4 regions. When the error is getting smaller, the speed of the motor will be slower also. So I thought this will be smarter than the previous approach. But then my question before I run the system with this kind of controller, why do I split it only with 4 different speed? Why don't I split it into 8, 10, 20, 50 different regions of speed, 100 or 1000, or even smarter, I split it into infinite number of region. If I have this kind of logic with infinite number of speed interval, how does my logic of the controller will look like? If I chunk it into infinite number of regions, my controller will look like this. So this basically is the same like the on-off controller, but I chunk the speed region into infinite number of regions. If I do it like this, apparently when I run my motor with this kind of logic in my controller, this is what I will get. When the position of the shaft is about to reach the target, the speed is getting slower, slower, and slower until it reaches the target, and then I stop the motor speed. Okay. Apparently, it works the best compared to the previous on-off controller. Okay, so let's talk a bit more detail about this kind of controller approach. If you look at the relationship between the U, right? U is the output of the controller, and the E, the error. So U is the output of the controller that it will be fed to the system that you control, and E is the error, the difference between R and C. If you look at the relationship between U and E, you will have a linear relationship. U is proportional to E in this case. And the proportion not necessarily to be unity proportion. You can have different gradient here to represent the relationship between U and E, and the gradient you can call it as Kp here. This kind of controller is the controller that we call as a proportional controller. Why we call it proportional? Because the relationship between U and E is proportional.